So today's discussion is going to be about hardware and hardware acceleration. So I prepared a couple slides more to just kind of orient us and get us started to frame the conversation versus to actually structure the whole conversation. So these are mostly from my brain. If you see something that I've missed or is wrong or is confusing, please feel free to raise your hand, correct me, ask questions. Any of those things is awesome. So with that, I will go ahead and get us started here. And like I said, the slides are not beautiful, but the host is disabled screen sharing. So if I can get screen sharing, Mr. Ted, I would greatly appreciate that. I forget how to do that.
Got it.
Oh, look at that. Beautiful. Thank you. So the agenda today is going to be really the three major slides that I wanted to kind of walk us through, open up with what is hardware acceleration, kind of what's the history of that, and then talk about some of the emerging technologies that have been coming out the last, really focusing on the last year or so, because there's been just so much change in the last year. And I've given some prompts for ideas on some of the discussion there. I'll go ahead and jump into kind of my definition of what hardware acceleration is. Please note, again, these were all voice dictated on the way here in the car, so there may be misspellings. But again, so AI in general is whether it's neural networks, Bayes nets, decision trees, it's going to be both memory and computationally expensive. And so the history of AI acceleration has been long and storied and has been kind of dead ends at various times. But they're kind of, I tried to boil it down into three major techniques. The first being memory and memory pipeline acceleration. This is like when you think about LLMs, large language model, the fact that it's large means that it's very difficult to fit into memory. And so putting things into memory, taking it out of memory, putting it into memory, and then moving it to the compute block, all of those things are very important. In fact, if you recall, like for the last 20 years, the dominant player in AI has been Google, and Google's biggest contribution really what was to not do this. It was the type of storage called NoSQL, Hadoop type storage, which essentially you move the compute to where the data are stored instead of moving the data around as much as possible. And that was, this invention from whatever that was, 1998, 1999-ish timeframe. And it dominated all machine learning because it was information retrieval for like 20 years. And so that was a huge kind of slowdown in the rest of memory optimization. But as we move into this neural network deep learning space, memory and memory pipeline acceleration are again becoming very, very important. Technique two is general compute, linear algebra acceleration, making CPUs faster, making them parallel, making them able to do more computations in a short period of time, whether that's sequentially or parallel, making the types of compute that they do more refined. And so that's why things like the specific integer math and floating point math has those specific compute modules, which are kind of reduced to transistors. If you can do it with fewer transistors, you can do it with smaller transistors. That really impacts how well the AI will run. The third technique is I didn't quite know how to call this, but like special operations. This has been around for a long time. It always, every time there's a new type of AI that arrives, this is the first thing people think about, and it always fades away pretty quickly. That's not to say that it won't eventually be like the thing, but it's kind of like the redheaded stepchild of AI for the last 30 years, which is FPGAs. And so you go back into the 90s where we were doing fully connected neural networks. This is not actual kind of connected, fully connected networks, associative networks. And FPGAs were all the rage for like 2.5 years, right up until the cost benefit made them irrelevant. Same thing happened in the late 90s when Bayes nets emerged. Same things happened during the early phases of MapReduce, Hadoop type computation. And again, gone. In fact, FPGAs were around right in the mid 2000s. There was a company called Netezza where they made custom hardware for SQL queries to accelerate data analysis and computation. Again, emerged and then disappeared because you guys don't know what Netezza is. I think that's a really good example of the cycle of this. Something similar happened in deep learning. There's a company that I mentioned later on called Nirvana. Same thing, emerge and then disappear. Dev,
I
driver,
I thought
driver Dev, apparently. Are you driving right now or are you in an Uber?
uh,
Oh
Tesla
shit.
is driving.
Wrong answer. Okay, go ahead.
So Natira, I thought that got bought over by IBM for $1.5 billion. Isn't that right?
It did. And then it got erased.
Yeah. Well, whatever IBM did is subsequent to
Mm.
that, but at the peak of it, they actually were doing pretty okay. Yes, but you're right that they were making custom hardware. And the reason I know is I was in the competing company, which was all software based for
Oh,
SQL, MPV SQL, Astrodata. So
oh,
that's
I
how I
didn't
know
even
about
mention
Natija.
Astrodata. I'm sorry. I mean, Astrodata does deserve a small mention. It was a big player. Yeah, Netezza was cool. I was actually one of their advisors, and Netezza had this really neat feature where sometimes its results were wrong. It was unpredictable and completely inconsistent when it was wrong, but it did one thing really consistently when it was wrong, which is that it was really, 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 really wrong. So it would be like, count the rows in this table, and instead of coming back with six, it'd be like 45 trillion, 896 billion. It's, 392.1. And you'd be like, okay, that's entirely the wrong set of dimensions. Like you can't have zero point 0.1 rows in a database. And
Hmm.
and that's way off. And so it was really good that when it was wrong, it was so wrong that you could know it. And so we had this wrapper that we wrote at Amazon where we'd run the query twice, and if the answers were different, then we'd run it a third time and then do voting. Um, but it did have its issues, I guess, is my point. But yeah, I mean,
Yeah.
Netezza, when IBM bought them, they were unable to continue to scale that because the precise hardware specific type of acceleration that they were doing just didn't scale the general purpose.
Yeah. And after the financial crisis in 2007, basically all the companies with custom hardware, they didn't have much to survive on.
Yep,
So that
that's
is
right.
true.
The data lake world, that MapReduce moved the compute to the data model. It became the dominant feature for
Mm.
everyone for quite a time.
Yeah, and same happened with Nirvana, the cloud storage. I don't know why they didn't. I really don't know why they didn't take off, but maybe you have more know-how about that.
Yeah, I mean, we can talk about that one in just a second. I'm going to come back to Nirvana in a second. Um, so anyway, the third technology, it's fun. It's fun to talk about. Like the hardware precise, specific hardware acceleration stuff is always some of the neatest stuff. It's almost always the fastest for a very short period of time, and then it kind of goes away. Um, and then some things that are on the horizon, just to kind of to get our brains starting to think about kind of what we could talk about today. Optical processors, those tend to rear their heads every once in a while. Like, can you use light instead of electricity for various reasons? It's more parallelizable, or it's faster, or whatever. Organic processors, these tend to rear their heads mostly from kind of the neuroscience side of AI, especially when neural networks start taking off again. People talk about organic processors. And organic processors I'm not very familiar with them, so if anyone knows more, but generally they are better at doing associative type networks than silicon and those types of more rigid processors. But there may be more benefits to it that I'm not aware of. And then finally, quantum processors, which I think those are far enough in the future that unless somebody has something specific, I would just again use that to seed our brains. Any other thoughts or feedback on kind of my question about what, and then I'll go to the history. Okay, so this is again David Sellinger's personal view of history. So if I've missed something or I'm wrong, feel free to add. I would always start out with like we started off with the traditional CPU plus hard disk drives plus memory. Then we had early FPGAs. One of the coolest early hardware specific solutions was the network memory computer. This is was most exemplified by a company called Silicon Graphics, which was a super darling during the very first dot-com 1994 through 99-ish timeframe. And they built these massive computers that had terabytes of RAM. And if you happen to have $150 million lying around, you could buy one yourself. And they did. These guys were known for selling to organizations that had three letters. Sometimes they would take orders. One of the greatest stories amongst the people at Silicon Graphics was they would take orders sometimes in cash. Like they'd have like $10 million of cash dropped off. And then the delivery instructions would say, leave them on the dock at 3 a.m. And then the computers would be gone the next day. And nobody would know where they went. So they had those types of customers. It's really kind of a neat time if you happen to work there. Really scary if you happen to be anybody else. Next up, I'm going to jump pretty far forward because from a hardware perspective, the next phase was pretty much dominated by MapReduce, which really didn't have a ton of hardware acceleration as far as I know. There was SSDs, which had a huge impact on all sort of information retrieval. But the next thing I'm going to jump to is CUDA, which CUDA is the library within NVIDIA that allows for linear algebra acceleration in the floating point center. Those come from a type of math that are used by graphics to do shading, meaning that in this pixel, what color is it? What object am I hitting? And approximately how dark or light will it be relative to the pixels next to it? And so those shaders can also be used, or not can also be, those shaders are fundamentally linear algebra computational units. And the interesting thing about CUDA specifically is that CUDA is actually not as fast as a CPU. Its clock cycle is way slower than a CPU, but it's designed to do 1,000 or 10,000 computations all in parallel, which again, for linear algebra, if you have a matrix that has 1,000 rows and 100 columns, then that's a phenomenal fit for, I'm going to perform this one operation 100,000 times, 1,000,000 times, 10 million times. And even though each operation takes, let's say, 1 millisecond versus a 4.3 gigahertz CPU, which is going to go way faster, it's able to do that 1,000,000 times in that 1 millisecond. And so that introduces the concept of flops versus hertz. And this is kind of one of the first ones that became really popularized. The next step was CUDA-NN. This is a little bit less about hardware and more about software, in that it's a special software layer sitting on top of CUDA to optimize those operations specifically for deep neural networks, though it is very hardware specific, so I thought it was worth mentioning. Then we have memory pipeline optimization for neural networks. This is things like optimization of the PCIe bus that moves data between the computer, the CPU's main memory, and the memory that exists in the graphics cards, which are used for neural network training. That also got applied at some specialized hardware companies, but memory became quickly the bottleneck. Once we moved into this modality where we're doing big flops of linear algebra, then memory pipeline became the bottleneck for almost, I think, almost all neural network training operations. Then the next step in hardware was discretization. Because floating point math was the origins of all neural networks, floating point math is very complex in a CPU or any sort of silicon. The representation of floating point numbers is not direct. You're actually, I believe it's a base and a mantissa, right? Is that the correct way to kind of think about it? And so the way to compute it is actually multiple steps and pretty complex for any sort of linear algebra operation. Anybody know more about that to share? Because the next step here is moving to integer math, which is way faster and is typically one clock cycle per computation. I would really welcome anybody who knows more about this than me to share that one. Anybody?
I mean, I don't know much, but I mean, if you just say like 4.2 times 10 to the third, and you multiply that by whatever, 6.5 times, 10 to the fifth or whatever, then sure, you can add your exponents together and you can multiply the 4.2 and the 6 point whatever I said together. But if you get 20 something, then it's like, the carrying business. You now need to shift it down to, 2 point something and then whatever. So it's binary instead of decimal, but still, those are the things you got to do.
And even 4.2, like even without the exponent, 4.2 times 6.4 in silicon is much more complex than integer math. And I believe even that chunk takes like 2 or 3 clock cycles, whereas again, integer math is generally kind of a single clock cycle per operation. And so as we move into the discretization models, integers are lower memory. So a general floating point would be like floating point 64 bits versus an integer 16 or even an integer 8, which are now being used for neural network training, which means 8 bits instead of 64 bits for every operation. Just a lot faster to move your memory around. You can have a lot more data in memory. I think the right way to probably articulate that would be you could have a lot more um, neurons in memory because neurons are smaller. So discretization's been a huge transition. The first really well notable version of discretization was the TPU from Google, and then recently, as more and more applications are arising, we're seeing inference only accelerators. Those are like the first one I was aware of would be an inference only accelerator with proprietary software made by Qualcomm. So the Qualcomm Snapdragons came with a special library that you could convert about 5% of TensorFlow models into their special model format and then run it on Qualcomm, and it would accelerate it using the GPU, and it had an onboard DSP, and it would do all its acceleration only for inference, not for training time, but you could do a ton of acceleration. You had to know their special libraries. You had to convert the code. The libraries only supported a limited number of operations. And then where that would bring us to, actually, and I spelled this wrong here, would be TF Lite. Recently, TF Lite and a couple of other standardized libraries have emerged where those standard libraries run on a whole bunch of different specialized hardware. And that would be kind of where I think we are reasonably today. So in terms of the conversation today, I would be open to talking about any of these. I think there's a lot of stuff happening on all of them. There's training, there's inference only stuff that's going on. Nirvana is a company that was down in San Diego and was acquired and then kind of wiped out by, I think it was Intel that wiped them out. Zluda, if you followed that one, that spiked in the news about 6 or 8 weeks ago and then disappeared promptly when NVIDIA made it breach of contract to use it. Very nice of them. You wouldn't call that anti-competitive in any way, would you? And then ROCm, which has been AMD's, that would be like me. It's the bald, redheaded stepchild of your ex. That would be kind of how I would describe ROCm. It's been around for about 9 years at AMD. It's an open source project with the only contributor being AMD, and AMD seems to have forgotten about it for the last 8 years. But it emerged again a couple years ago. They always make this big to do, like they're going to do something, and then nothing happens. So I'll continue to mention it. Halo is one of the discrete. They make an M.2 accelerator board that apparently does like 26 flops. If you compare that with Google's Coral TPU, that does, I think, 8 flops. And so it's way, way, way faster. I don't know if it actually works. And then there's a bunch of NPUs. I don't know what NPU actually stands for. NPUs are things like there's a SoC manufacturer. SoC is system on a chip. That's basically the people that make chips that run in your Android phone. That's actually kind of the general use case for it. One of the larger one is a is a chip manufacturer called Rockchip. It's a Chinese company, and they make the RK line uh, 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 SoCs, which is the CPU. Generally, they're ARM based, and they run little single base board computers or cell phones. And they added a module called an NPU to their SoCs, and then they added libraries so that you can run TF Lite on them. Rockchip is the one that I know the best, just because it's a very high volume manufacturer. They have tons and tons of phones, tons of devices out there that run Rockchip, and Rockchip recently added an NPU and AI library for them. That is inference only as far as I know. But those are some of the things that I would use to kind of kick off the conversation and hear questions or ideas or things that other people have heard. So I hope that was useful and made sense and helpful for kind of kicking off the conversation, but I'd love to hear questions and ideas from folks. Maybe I can ask.
Couple things.
Yeah.
Couple things that come to mind is, AWS has also jumped on this, right? With their, I think they call it Trainium and Inferentium, very sort of, like very clever names on them. They
Depends
don't
on your
run
definition
CUDA.
of clever, but yeah.
Right. Yeah, I was being facetious. And they don't run CUDA. You have to run some conversion on them. You have to take your code, and they can only, if they see a bird or a llama or something, then they have, depending on the model, they can convert it to their stack and then run it, something like that. And the two architectures are based, the base of the two are the same. And so basically, if I remember correctly, it's something like the number of compute units and the number of memory. They've kind of played with that to say, okay, this one is for training and this other one is for inference. So that was one thing. And then another
That's cool.
thing
I didn't know about that one. Thank you.
Yeah. And these other things where they have these large wafer AI thingamabobs, like this company called Cerebrus, I think.
Cerebrus.
Yeah, Cerebrus.
Yeah,
And
$500 million. Yeah.
Yeah, you know about that, right? Yeah, so they have like this whole wafer is one chip, one AI chip. There's another company called Rain, Clouds Rain.ai or something. So they also are trying to get into the space where they want to kind of scale out on the wafer and then come up with these really large chips. So those are things that came to mind. Also, like the Apple chips, M1, M2, M3, they have like the neural processing engine and things like that. So they're also using AI, but not sort of opening it up to people to use. But that's also, I think, would fall in this space, right?
So the M3 is actually going to be quite, what do you call? It's not going to be a game changer, but for the laptop thing, they probably will try to have something that you will run locally on your laptop for large models. So that is what they are going after. But they don't want to put it in the server. So they are against
that. Will they open it up?
I think they will. So the thing is, Meta is also doing, we are recording this, right? Yeah. Yeah, so there's something working from Meta also. So they are also trying to scale up on very large things. So they are like 3, 4. Cerebrus, the thing is, I'm going to get my friend is going to come for dinner. So that's why I won't be, I'll just tell what I know. so that you guys can kind of take it from there later on.
Please.
So Cerebrus, the problem is what happens is with the chip, the yield is pretty low. And so what they're trying to do is make sure that even if there are failures, they can route around it. So that is the trick that they're trying to play. So they say that eventually this will get so big. So if you are ready to invest $500,000 or $1 million on one box, so this is all you would need ever. And then we will, so the failures is what they, so most of the thing is going to be around the software layers that would happen. So there was a similar effort done for Gmail. Like they would do on Atom processors, you would put it on a small chip, a large array of them, just like the GPUs, and say that we will take that cost and there would be individual layers running on it. If there are failures, fuck it, like who cares? That attitude. The other one is when you look at the NVLink and the NV switch and all, you can say that, okay, can I have a private in-house cluster, which is like say $500,000 and that's all I will ever need. It'll be behind the firewall and I don't really care about it, right? So that market is, so I would really like, I don't want what I'm telling is a little bit sensitive, but the thing is what the data center guys are running into is the heat problem, the private guys. See, the Google and OpenAI, it's a different beast altogether, right? Meta and these guys are. The huge market which is there in the private data centers, their problem is that when you have these large chips, they cannot do the cooling. So what ends up happening is that for every rack that you do, you have to put in 8 things around it where you cannot, like, there's so much of heat getting through and then you have to cool it. And so the cost thing is not working out for them. And everybody says we want stuff, but nobody's ready to buy. They're sitting on the sidelines. So that part of it is, I believe that the moment Llama 3 comes out and people say, okay, we can have fine-tuned models and we can go pretty much in the private cluster, we're able to deploy it, you will see a big sync happening and you'll see a big adoption that is happening in the private, on the enterprise side of things. All the stuff we are talking of Google, all this forward-looking stuff, it's all okay. I mean, there's all other things. But my personal belief, Dave, is you probably don't need more than 3 or 4 custom LLMs with a backbone LLM, and they can be talking to each other. That is all they would need on the enterprise side of things, which are really fine-tuned. That market will grow, but it is still like the cost of it is so high that people are saying we are not really comfortable putting into it. So look at this company called Replicate. Go and try to understand what they're trying to do.
What's it called?
Because
Sachin?
what Replicate is that
Replicate.
Guys who came from Docker, right? And their take is that the GPUs are going to be expensive. This is a big game, and the smaller guys will never be able to kind of procure the GPUs. What will we do is we'll be the front end, right? We will be the front end, and we will have these GPUs on demand, on and off, and you will only pay the time when you're actually attached to the GPU, which is what the end customer wants. And we will work on that scale, but we don't want to work with any hardware vendor. So NVIDIA is pushing them to actually say, can you build custom solutions for us? And no, these guys are saying no. These are guys who are from the market is to, it's just people are just waiting to say, can we see a good adoption? And then you will see that going on. So Replicate is why I'm comfortable with Replicate is they have 30,000 paying customers today. And what they have is a cog. A cog is basically like an encapsulated entire Docker that you can basically put in, you do it and someone else can take over from there. So the Replicate, right? So, okay. So I'll listen to you guys, but I don't have anything more than to add because once my friend comes, it'll be very hard because I'm entertaining him for dinner. But okay, sorry about that.
Thank you for sharing.
Yeah.
So that was a lot on the training side. I contributed mostly on the kind of internal side, so I appreciate that.
Yeah.
Any other folks that have something they want to toss out there?
The
Anybody?
other thing I wanted to add was, I forgot his name. So he was talking about like power, right? So power is becoming like a major thing. And, the new memory for GPUs, HBM3E is the latest thing, So HBM123E. And so they basically, around the latest GPU from NVIDIA, there's like 8, HBM memories around it. It's crazy. And the power taken up by the memory is becoming significant. Before it was like all of the power was with the compute. But now with these being memory hogs and with so much memory being dumped on these chips, the power of the memory is becoming also important. So I think that memory also is starting to play a more important role in this whole, AI Wild West that we are in right now. Sorry, am I not coming through? Okay.
Just a little quiet.
Okay. I hope you heard what I said. Yeah.
Yep.
Okay. Yeah.
So anybody, so
Also,
those are, go ahead, please.
yeah, also the NV, is this better?
Much.
Also, oh, thanks. Also the NV link that he was mentioning, I don't know much about it, but it's like, using multiple GPUs on a single host. That is also, plays a part in, I think they're
Yeah.
trying to like
So I can
scale
talk.
any which way.
I'll tell you about NV Link and NV Switch. So the next generation is the NV Switch that comes through. But these systems like you cannot get unless you have a huge account. So they will not sell you NV Link systems. So remember, Dave, like few years back, when I talked to you about like buying the 5 PCI wide cluster, right? And you said like do a very small one and let it go kind of, and eventually I built a large box. They would not even get me an NV Link. The guy says that unless you do like 100K business with us, we don't even want to talk to you. You have no idea how many POs I talked to 40 system integrators. And finally, I ended up buying a server board and a thing which is about $4,000. And he sold me at a premium. And that too at a premium because I knew the vendor and things like that. So these guys are like minting money, and NV Link, NV Switch and all is again the $500,000 business kind of a thing. So for common guys like us, when we are trying to do this, is like back to mainframe business, right? You want an environment in which you can replicate on your local one, be able to put it out, fine tune with say in $20, $100 or whatever it is, get the thing out, and then again play around with it. So that is, I believe, what the market will happen. So I will maybe 2 months down the line, I will do a distributed GPU training session, but it'll be like pretty very closed version of it. I won't do it to very few people. I will show that. So okay, so because I'm kind of looking at that market a lot, where you do this and basically deploy it behind the firewall in
And I
completely
think
operation.
just so folks know, I'm going to throw out what I think NV Link is for correction. It's a fiber backed, right? It's a fiber backed abstraction layer that basically allows you to have multiple racks of GPUs that all operate under the same host and operate with the same, again, kind of abstraction layer for memory. So you as a data scientist don't have to deal with all the routing and stuff. Is that correct?
Yes, that's correct. That's absolutely correct. And the next generation of it, what is they're calling is the NV switch, which is like the higher one. So what NVIDIA is doing is it is investing in terabyte business, terabit basically interconnects. So they are trying to like, so that is where you can see where it is going, right? So they are saying we'll build the fastest, what you call, interconnects across these things, and these guys will work in what you call cooperation, the GPUs. So the
Got it.
distributed training
So
is what it
essentially,
will be.
NVIDIA's just said with what their bet is that memory is the next threshold, not compute necessarily.
Correct. Correct.
Memory being interconnect. Okay.
Yeah.
Got
Yeah.
it.
Yeah.
Very cool. Ted, what you have your hand raised?
Yeah, so I don't I don't follow the hardware side of things too much, but a couple comments on just sort of the software side. So like you mentioned like cuDNN and some of the other things you mentioned, really like I've had people share with me and they said that if AMD can build a chip that can do matrix multiply 10% faster than an NVIDIA chip, your actual ML model will still run 10% slower on it because that, ROCm, whatever, drivers, the software is not as good as the years that have been poured into the NVIDIA software. And so even though the hardware is faster, if you don't get the software right, then you're still operating at like a 25% penalty.
Yep.
So I thought that was like a really interesting comment.
Yeah, I mean, cuDNN is a lot of people don't realize how massively impactful cuDNN is. I want to say it's on the order of 100% boost relative to just straight linear algebra.
Yeah.
And the testing point for this was about 5 or 6 years ago. TensorFlow launched support for a competing acceleration called OpenCL. And the reason it didn't make it into the history is because that ended up being one of those kind of like dead ends that didn't go anywhere. And OpenCL is the competing model for OpenGL, but it's for the compute side of the graphics acceleration. And you can use OpenCL to do the linear algebra acceleration, which is effectively kind of equivalent to ROCm or CUDA, but does not have that neural network acceleration layer. And so even if you had a card that was twice as fast and you used OpenCL, it would still be faster to use 2 generations old NVIDIA cards because they had access to cuDNN, which in my view, if we can go to kind of anti-competitive, is why Zoluda was one of the most impactful and interesting, like quick chapters of neural network history. Because Zoluda, if you don't know what it is a like for like replacement for CUDA, meaning that you could use cuDNN on top of AMD, Intel, and I think there was one other, was it ARM hardware for like 35 seconds. And then NVIDIA said it's a violation of all of our terms of service. If you're caught doing this, we will, kill you and burn you to the ground, even though I'm Jensen Huang and I'm a really nice guy and I'm from Taiwan. But yeah, so that one, I think I got that reasonably right. Is that
Yeah, and I'm not sure if this is exactly right, but like the way I think about it is in the computer graphics world, predominantly what you're talking about is 3D objects with 2D surfaces that are lit by what's modeled as point light sources. So the dimensionality of the matrices that you're multiplying in order to calculate the textures and the lighting and all that, that's sort of like this known thing. But once you get into deep neural networks, then we're talking about tensors that are more than 3-dimensional, and we're doing a lot more math. And so my high level picture, and I don't know if I have this exactly right, but basically, if you have a matrix A and you multiply it by a matrix B, and let's just stick with 2 by 2 for now, then essentially you would like matrix A to be laid out physically by rows. and you want matrix B to be laid out physically by columns, because that's how you do the matrix multiply. Okay, so you can decide that you're going to physically lay out A that way and B that way. But later on, if you multiply something by A and A's on the right, now you're screwed because you physically laid it out in rows, but you want it physically laid out in columns. Okay, and so part of the optimization is you have to look and see how many times am I going to use A on the left, how many times I'm going to do it on the right, and you have to do this not just for 2-dimensional matrices, but sometimes 4, 5, 6-dimensional, once you throw in like batches and this and that. And then sometimes I'm going to calculate a softmax this way, and sometimes I'm going to do normalization this way. And so that's where, you know, I guess that's my understanding is where it gets hard. There was actually a Kaggle competition to sort of say, here's a computation graph, and it starts out with these, whatever, like, you know, 10 objects that you're going to multiply and add and do stuff with. So say up front how you want to lay out each of the 10, and then we'll see who completes their code the fastest. And it's not a solved problem.
So Mo has a question here, which is this for memory locality optimization? It is, as far as I know, it is both for memory optimization as well as it is for computational optimization, because you also may apply a computation at one point, use its result, and then throw it away, and then reapply that in the computational graph. And so to Ted's point, it's full graph analysis. It's reordering operations. It's storing and caching data. In some cases, it would be like when convolutional neural networks first appeared, the biggest update to cuDNN was when CNNs took off right after AlexNet. They actually made optimizations specifically for convolutional operations.
Yeah.
Jan,
Yeah, I am beyond my depth, but you can imagine that if you do a row times a column and you break it up into chunks, then like you can load one part of the row and you can just leave it in your processing unit, and then you can pass in multiple chunks from the column. Okay, but then there's the next layer of that, which is you take those outputs, and some of them might fit in memory for a little while, and so you want to like be able to reuse stuff and not have to ship it back out to memory and then reload it when you need to like add up all of the pieces from the column or whatever. And that's why ordering matters, because otherwise theoretically you're sort of always taking the same number of patches and multiplying by the same number of patches. You just want them to happen to be lying around in, I don't know what they're called, but registers, as opposed to having to go and fetch them from memory.
It's VRAM, but yeah. I mean, yes, there is the register layer, but for the most part, what cuDNN's optimizing is the VRAM versus the system RAM. But there is that also the register layer. Jant.
Yeah, so I was thinking about, Ted, what you said about the, laying out the matrices. So couldn't all matrices be laid out, like row wise? And you do the multiplication, under the hood, like the way we have all been taught matrix multiplication is, row column. But that's just maybe for us to make it easy for us to understand. But that doesn't necessarily mean that's how hardware should do it, right? Because under the hood, it could still imagine that the matrix on the right is you go column, and then couldn't that work?
So again, like the idea is if you take a row and you multiply it by a column, if you have a chunk of that row, then you can just loop through all the chunks of that column, and you never have to do a load from memory for the row part. But it's not just that, it's then the products that you create have to then be added and merged and whatever. You want those local. If you just went in any order, you would get the correct result. But if I just started pulling random chunks of the first matrix and then random chunks of the second matrix and multiplying them, you would run out of memory, and you'd have to push those results, intermediate results, out to memory, to HBM, and store them until you could then come back around and sum them or whatever the heck you have to do with them. And that's what costs you, because apparently you can do like 1,000 matrix multiplies in the times it takes you just to shove one chunk into HBM.
Yeah. So yeah, I mean, I was on second thought. I guess you could do it the way I was thinking, but you'll have to double up the memory, which is no good.
Yeah, so that was what I was gonna say. Is it really comes down to what you're holding at any one point in time. It's not really the representation. It's what are you holding? How long are you holding it? And then again, like apply this in the context of flops, where every operation that Ted and you were talking about, it's not a single operation. It's applied to some n-dimensional a matrix, and so you're doing it a million times in parallel and flopping across. And I don't know if other people are getting that visual from me, but that's the way that I always imagine the difference between a CPU, which is kind of like a pipeline. So it's a kind of a manufacturing pipeline versus a GPU, which is like these big pages flipping. Every time you do something, you have to do it a million times. And if you have to turn two different pages, that's way less efficient in a GPU, because even if it's the same amount of words, because it's two pages, the GPU just handles that less efficiently.
Yeah, and I don't really know how things work like down in silicon. Maybe there's even some other kind of concept like they don't just have one matrix multiply unit, right? They have like hundreds or thousands of them. So maybe there's a way where you like distribute your row across these cores, and then the column comes in and it just rotates, shuffles through them, and all of those outputs are just sort of all immediately there, sitting on your hundreds of cores, and they can then get summed together. And it's super fast, but like we're saying, if you instead laid it out the other way, you'd have to bring things in, put it out, because you can't just hold all of them like Selly's saying. You want to be able to reuse those things and get them out and not have to be hanging on to them for future use later.
Anybody have any insights into the inference space? The TPUs, the NPUs, SOCs? Anybody? This is where a lot of the money's gone recently. No? Grok. I don't even know what LPU is. Dev, what's LPU? They parallelize data flow.
I think L is language.
Yeah, language or LLM processing unit. Oh, I don't know exactly what they call it, but they have pivoted a few times, and the latest pivot is LLM processing unit, essentially for inferencing, and optimized unit for inferencing. And
I mean, if you have to do a pivot right now, that's what you should do, a pivot to LLM and then insert whatever word you want after that. In fact, you should probably ask an LLM what word goes after that when doing pivots. Sorry, go ahead, Steph.
Generative AI is the other pivot.
GPT-4o can give a lot of ideas on that, but going to LLM or LPU. So I think what they did was, looking at the, I think they do some optimization with respect to the tokens flow, and I don't know exactly how they do it. I've listened to one of the talks a few months ago, and I've forgotten about it, to be honest, but they make sure that the hardware is fully utilized while they are doing multi-users, big batches inferencing, by ensuring that they're, oh my God, I shouldn't say anything without recalling what they did. So, but it's optimized for LLM, and they do some specific data flow optimizations. Beyond that, I have to look back to their talks and say that, sorry, I brought it up, but I don't know more details about it. But they are specifically focused on LLM processing units, optimizations for big deployments for multi-users, like companies like Fireworks and Hugging Face, for that matter, right? If they want to, like, they do give this free inferencing to a lot of people, right? Go and try it. But at the end of the day, the idea is that someone will purchase services from them. And if there are multiple users, they don't want their GPUs to be sitting idle. And this one unit can potentially have optimized only for inferencing. And that's what they're doing. Once you build the model, you're just deploying it for inferencing for their customers and optimizing for that. Again, not too many details here. It's at a very high level that I'm talking about. I mean, that,
But you're
I
saying
don't know
that,
if that helps
they're
with the
thinking
gist.
about
Yeah.
accelerating or costing, one of the two, the compute in memory specifically for LLMs.
Right.
Yeah, I mean, like
see,
fundamentally, right? GPT-3, Llama, like a lot of these models have almost identical architecture. So you can really like say, I'm going to devote my hardware to be optimized for exactly that architecture. And then something like Mistral comes along and then like FPGAs, you may suddenly be screwed. I'll mention
knowing
that
when to make that bet, that's hard.
Yeah. I'll mention that in addition to that side of it, there are people who are looking to design, models that are a little faster for inference. So for example, sometimes people fuse certain components. So if, the original model said do A, then B, then C, then D, then they're sort of like, oh, guess what? We'll let you do B and C in parallel, even though they're supposed to be sequential and and they're designing different algorithms for inference, right? And then one of the things that I thought that might not be a real risk, but it was kind of a bummer, were these people that showed that if they had access to the server, which you shouldn't ever have access to the server, but basically, right, they're running big batches, so of course they're running multiple users, and they were basically able to examine uninitialized GPU memory and extract your data out of it.
So
That
one
makes me
of
sad.
one of my observations has been that companies who have already paying customers and making money off of this are the ones we should kind of look at, because they know how to squeeze the request onto the GPU and convert it into money, right? Like the inference is where the money is, right? So if you look at Replicate, you look at what is the other one, Repellate or whatever, the browser-based code completion. The reason why they are in the browser-based is because they are providing you a sub-millisecond basically responses. The same thing, I think there is a Cursor company also. And what I've been hearing from them is they were in the business of trying to squeeze money out of the GPUs very early on, few years back, and they know the secret sauce how to actually get this together. And so they saw the business coming through where, hey, we can host this. Single customers will not be able to host it, and we can now be the bidder in between where we can make money off of it. Right? Today, you cannot, as a single guy, go and say that, hey, I'll be in the insurance business and make money off of it. Only when you host multiple people over there, you convert it into dollars, right? I think that is one of the key things we should look at these companies who are converting, have paid users. So that's the way I look at it most of the time. So sorry, it's like I'm a little bit blunt, but
Thanks, Sachin. Janth.
Yeah, the other thing I wanted to mention is, what's happening in the edge, LLMs on the edge. I don't know if we'll get to see the under the hood part of it, but Apple is trying to do LLM on the edge, according to some reports, and then I'm sure Samsung, Google, these guys will try it. And these things are becoming part of the OS, which is really, the next level to me. Like even
Now you sound like a
like
VC. or an MBA? My gosh.
Uh,
Sorry.
well,
That was rude.
I am neither. So, you know, for
I'm just joking.
for full disclosure, I'm neither. So, and you know, like the Google, what is it, the circle, and you know, recognize or whatever. So all it is to me is like just building that circling thing into the OS. The backend is already there. It's probably Google image search. And all you have to do is cut that image. And so the thing is, the OS is getting more and more of these AI features into them. So yeah, so those are the two things I wanted to mention.
Yeah, you know, when I refer to inference, I'm always thinking about edge because that's my personal model through our company. And it's interesting because you know most of the conversation here has been about essentially cloud inference. But it is interesting how disparate the optimizations are for those two now. And then
Right.
Mo popped an article in the chat here that looks like this is the one for the uninitialized register attack. Man, it's so if anyone's read that, does that actually take advantage of like the noise across the transistors to just statistically guess what the value of the register is supposed to be? Is that what it's doing? That's scary if that is.
I'm not sure, but I think I'm going to study this after this meeting. It seems
Yeah,
pretty
that one.
interesting. Well, crazy.
If anybody did anybody read Cryptonomicon? Anybody? Oh, come on. A bunch of nerds and none of us have. Okay, well, homework for everyone is to read Cryptonomicon by Neil Stevenson if you haven't done that, because in that one they talk about something similar with monitors, but those are CRTs, which are no longer around. Oh wait, Jant, you had a question before you go? Your hand went up. Oh,
No, that was my hand from before.
oh
Sorry.
okay. Thanks for joining, man. All right.
Yeah, thanks.
I would
Thanks
love
for setting it up. Bye.
Yeah, thank you. Anybody have any other questions or thoughts about Edge? Because I think that is going to be an interesting, and so far as kind of user facing applications, I think that'll be one of the more transformative ones. Anybody see anything cool? Apple, Samsung, Google. All right. If we're there, does anybody have any other questions? Otherwise, I think, you know, we'll end a little bit early today, but I definitely enjoyed learning about I took a bunch of notes on these. The ones that Jayant and Sachin mentioned, Rain.ai, the Apple. Apparently, I learned about AWS, and I never thought I'd have somebody in the forum teaching about AWS, but that was awesome. Oh, cool. Dev mentioned a chip from Google I/O called potentially Trillium. Anything else from anybody though? Yeah, data center. Oh, it's data center. Okay. More data center, more data center. Yeah, Google's CEO is super popular right now. Oh, cool. Thank you, Ted, for sharing that paper as well. All right. Well, if nobody else has any more questions, I think we're good to wrap for today. Thank you guys for joining us. I will pop the Slack invite into chat if anybody wants to join. Please do. And we're always looking for presenters. I don't think we have a presenter yet figured out for next